Okay, this is lecture 45 on embedded maximality by Harvey Friedman. Please.
Thank you. So I've gotten to, by the way, can you see my face?
Yes.
Okay, good. I can't see any of your faces because I probably don't know how to do that. But anyways, I don't usually see your faces anyways that much. Anyways, so all right. So I have completely reworked, and I'm very happy with the way I'm doing this. I didn't quite finish checking it, and there may need to be needing it to add a dimensions in here, but it's not basically too serious if there's something wrong here. But I think it's I've almost so next week everything will be settled with more details about this. Uh, and okay, so let me go through what's going on here. So uh, my scroll. Okay, there we are. Yeah. So the book's name is constant, and the chapters are constant. The table of contents for this chapter 5, which is the finite stuff, the chapter 5 title, finite embedded maximality. Um, uh, so I actually start off with a variant. I think we talked about this last time. I'll review it. We have an embedded maximality variant that's very close to what was reversed. Uh, you'll see the difference. The difference is I multiply through by the number n. And that means that the indiscernibles in the statement reversed are the number 0 divided by n, dot, 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 n divided by n. And the here the indiscernibles are 0, dot, 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 n, just integers. Yeah, just so you multiply by through by n, so to speak. So this EMV is embedded maximality variant is a kind of trivial thing, but it's important for what I want to do to have to have those as the integers pulled out of the space is a very good idea. All right. Then there's a thing called finite embedded maximality. I now call it FEM, FEM. And FEM is the highlight. Uh, and is um, FEM is explicitly pi 02. FEM is explicitly pi 02. And so one wants also to have pi 01. So I have two different versions, two refinements of FEM. One is I just put a cardinality on the object that FEM is talking about. I just put a bound on the cardinality. And then it's still only explicitly pi 02, but you can use the machine of the decision procedure for the rationals with order, the usual thing, to know that this is explicitly pi 01, is pi 01 modulo the decision procedure. So FEM's sharp is already uh, uh, what we want. However, we can do better even. It's not difficult to do better and actually make this explicitly pi 01 without any real complication. Just flat out, explicitly pi 01 without any issue. And you'll see that. Uh, the let's see, back to here, the EMV. Yeah, I think I show up here that EMV is equivalent. EMV is equivalent to uh, the IEU. Uh, yeah, IEU identity extended usability. Yeah, so I didn't quite say this title doesn't carry exactly what's in there. Um, okay, so um, let's see, where do I show? Yeah. In this section, I show that these are equivalent. So all these variants are equivalent. and that proof is done in EFA, exponential function arithmetic. Those are all equivalent, and by elementary arguments of various kinds there, and then I want to start reversing these. So I want to show that I want to show that these things are all strong. All these things are strong. So I develop a thing called embedded resolution sequences. These approximate uh, these approximate EMB. These are approximate forms of EMB, and I call these embedded resolution sequences ERS. And I show that EMV is equivalent to ERS. And this is really uh, a compactness or a weak Kernig's lemma kind of argument. Could that these finite pieces give you the whole thing, and when you do it, for infinite length from the finite pieces, you get something that's pretty easily seen to be equivalent to EMB. All right. Now, the big deal is, and this is what I didn't finish, that I'm in the middle of, that FEM implies ERS. That's the crucial point. That from the finite form, I can get ERSs, I get the embedded resolution sequences, and then from then I can get everything I want. Yeah, so I will know pretty soon whether I have to make this FEM a little bit more complicated, but basically it's under control. It should be. So I'll see exactly what's going on for next week. Then there's a section which I've only been thinking about a little bit. I sort of know that this is going to be good. See, this stuff 5.1 through 5.9 with this FEM, you'll see FEM is really quite nice mathematically, is the mathematical stuff, but the algorithm, and so the audience for that is combinatorial mathematicians. But the non-deterministic algorithm approach is very friendly for computer science people, algorithm people, because the algorithm that I write down is in many ways a lot simpler than a lot of algorithms that people routinely study, even at the undergraduate level in a computer science department. So this is an interesting addition, and this will be there's likely to be more sections than that. I haven't really started that, and then we'll be done with chapter 5. Then the time is. Then we have to go. Then we're going to go to chapter 2 and recast existing work on standard mathematical objects, piecewise linear and semi-algebraic, whatever. These are going to be rethought in terms of embeddings. So the book is more strongly unified. You start off with some pure core mathematics of a mildly interesting kind, actually somewhat interesting, more than mildly at one point, because of that new result in that surfaced uh, about uh, semi-algebraic sets in 2 dimensions. Um, so I have to see how all that fits together with everything else. But so then the chapter 2, and then chapter 6 on the game theory, and then the book is done. All right, so here's the embedded maximality variant. First of all, we need some terminology. So this whole thing also needs a little different terminology. Okay, suppose I have a relation on any set X. In the relation, we say that S resolves X. S resolves X if and only if, first of all, S is contained in X. Oh, there's 2 different X's here. Yeah, this is a small x, and that's a capital X. If and only if x is contained in the space, capital X, and either x is an S, that's that certainly resolves it in some sense. Either x is an S, or when you put x in S, it's no longer a chain. Okay, that's the definition. That's a kind of a neat definition. Okay, so then you can prove that this is actually equivalent to the notion of maximal chain. So S is a maximal chain if and only if S resolves all points. Okay, so being a maximal chain just means that you resolve all points. Um, Probably this is not really right. If and only if S is a chain that resolves all points. And since I'm just stating everything elementarily, maybe I should say that. But yeah, that's what I meant to say. So your maximal chain, if known as your chain that resolves all points, it's a very natural idea. Okay, and now we have the notion of P shift embedded, which we talked about last time, which is a special case of my usability kind of ideas, right? And it's the one that's closely related to what was reversed in chapter 4. And so this says that if I have x in minus n 0 through n minus 1, and you replace 0 through n minus 1 by their successors, 1 through n, you don't change membership in S. You get this. Ah, okay, just a second here. All right. Okay, now EMV is every order invariant relation on every minus n to the k has a p shift embedded chain which resolves every point. I could have just said has a p shift embedded maximal chain. I could just say that, but I want to bring in this resolution concept because when I go to the finite form, I need this kind of English construction. I need this kind of notion in order for the thing to make the most sense. Okay. So that's what EMV is. Okay. Now we review some. Now I did a lot of this last time, so I'm going to do this real quickly. So we have the notion of F embedded and F usable from the earlier work. The identity extension. We had the identity extension usability theorem, which is the lead statement in embedded maximality. We're now doing finite embedded maximality, but the lead statement in embedded maximality is IEU. Um, and This is the definition used in chapter 3, and then that supports this. This is the chapter 4 reversal that minus 1, 0, 0 divided by k through k divided by k being k usable uh, implies con SRP. Is that right? Yeah. Yeah, that's what actually how the reversal works. Yeah. Yeah, that's right. Okay, so because the dimension and the length of the indiscernibles with what the k in there and the k in there are the same. Is that's what that was about? That I did a little more than I had to, like that in chapter 4 reversal. Okay, so now we multiply everything through by n. So we have these functions minus n 0 0 through n, and of course, we want to say that when we multiply through by n, that's exactly what's going on. N times that function is equal to this function, partial function. S is p shift embedded if and only if s divided by n is embedded in this sense. Then you can prove IEU implies EMV, and that's pretty clear because IEU is more general. It talks about the usability of uh, of quite a number of things, right? Now, the other direction, EMV implies IEU is not so clear, but you do get con SRP. And of course, with WKL naught, con SRP is the same, gives you IEU. So you do have this. I suppose there's a little bit of an open problem here. There definitely is, namely, is IEU and EMV equivalent over RCA naught? It's equivalent over WKL naught. So that's something, that it's a loose end a little bit. All right, now we come to the finite statement, the main event. And this requires an equivalence relation, or well, I actually call them associates. So X and Y are associates if they have the same order type and they have the same integers in the same position. They have the same order type and the same integers in the same position. So now we're ready to state FEM. Every order invariant relation on every minus n to the k is has a finite p-shift embedded chain that resolves an associate of every point. And compare that with EMV, which says every order invariant relation on every minus n to the k has a p-shift embedded chain, so far it's the same, that resolves every point. So instead of saying resolving every point, and that forces it to be maybe infinite, instead of saying that it resolves every point, you say that it resolves an associate of every point. Resolves an associate of every point. That's what I'm saying. And so therefore, this is a very friendly finite form, I think. I hope I don't have to actually make this more multidimensional than it is. I have to, I have to check that, but I'm hoping that this is exactly what I can do. Okay, now this is obviously explicitly pi 02, right? Because you're asking for uh, a finite object. So that's the wait a minute. Should I say? Wait a minute. Let me see. Every order variant has a finite thing which resolves an associate of every point. Yeah, I guess there's some work needed to do that. I guess if you don't do any work, it's explicitly pi 04. So I think that I misspoke here, and but it's easy to to play around with this. Certainly, you can. Yeah, I think what's happening is this. I think FEM is explicitly pi 04, and it's explicit, and it's pi 02 modulo the uh, decision procedure for the rationals under order. Okay. Now, FEM sharp is explicitly pi 02, but if you use this FEM sharp, but if you use the decision procedure for the rationals with order, you can see it's pi 01. And then finally, FEM pi 01 is what I call it. Every order invariant relation on every piece, well, on this piece, and then to the k intersects z to the k divided by 3kn to the 2k has a finite p shift embedded chain. This is finite already. See, this intersection is finite. Has a finite p shift embedded chain that resolves an associate of every point. Yeah. I mean, there's some ambiguities. I think they're threatened ambiguities, not really. What are the points here? The points are the elements in here. These are the points. But I could take the points to be anything in minus n to the k, because I'm only talking about associates. You see, the associates are always association is equivalence relation. So there's some leeway here. But by point I really meant these points in here. Okay. So that's explicitly pi 0, 1. There's no issues. No unbounded quantifiers. Okay, so because association is an equivalence relation with finitely many equivalence classes, you just have to resolve finitely many things, finitely many points, right? But you got to make sure that the result is p-shift invariant, right? So there's this general lemma 542 that you can take a p-shift invariant set and have a little subset, and you can always make that little subset p-shift invariant without growing too much. That'll be needed in the next section. But you can keep it finite. If you have a finite subset of a p-shift invariant set, it has a superset that's finite that's still p-shift invariant. That's what this is basically showing. Now that I got it screwed up here. Yeah. Okay. Now we actually get that everything in sight is equivalent over PRA. These are all the finite statements. And the way I do that, so I review the statements. Here they are, those three. And I show that each one implies the next. And this requires some computation. So how do I show fem implies fem star? Sharp, not star, sharp. Well, I just have to take an element from every equivalence class under association and resolve that point. In other words, throw it in or block it. Throw it in or block it with respect to the order of relation in question. All right. But if I do that, I may not have it may not be p-shift embedded. But then from the previous lemma that we just talked about, you can always expand it to make it p-shift embedded, as long as it sits in a original space that's p-shift embedded, which we have here. Okay. And what's this number 3kn to the 2k? Well, that's an estimate, an upper bound on the number of it's an estimate on the number of equivalence classes under association. But there's something else going on here. There is a blow up. There is a modest blow up connected with trying to make it p-shift invariant. So I got to show that one has to show that all of that stays within reasonable expression. And the expression I chose for this is 3kn to the 2k. And it's far, far, far from optimal. However, I picked it so that it's beautiful on the page, just about as beautiful as it could be on the page. 3kn to the 2k. All right, so that's how this goes. The next one is that I can make the denominators. I can normalize the denominators uh, in the finite p-shift embedded chain. I can fool around with the denominators and have an isomorphism. This is a fairly easy to do. And that isomorphism is going to be total. You can make it extend to a total one. And so it's going to preserve p-shift embedded being a chain, being p-shift embedded being a chain, and resolving an associate of every point is going to be also preserved. You got to show all this, and that seems to be right. That seems to work nicely. I got the same estimate, 3kn to the 2k. This is a bigger quantity because there's another factor of k, but this was so lax and gentle that I could do it with this just hanging around my office. Okay. Now these things are equivalent to EFA. Um, yeah. So okay, I didn't want to put proofs in here. Yeah. All right. So there's some simple inequalities that are needed to do this. Make sure the number. How do I get 3kn to the 2k? I fiddled around and decided that this is the right way to go, the right expression for this. Uh, this is not what I really mean. I mean that these are all equivalent. Yeah. All right. Now, how do I the missing link here is to show that fem is strong, and I have to show that fem is strong. I develop an intermediate concept, an intermediate finite concept. Fem is a finite statement called ERS, or embedded resolution sequences. And there's some technical issues that come up, so I want to restrict the relation I am working on to be what's called a diagonal relation. Okay, so a vector, a tuple is diagonal if all of its coordinates are equal, and a relation is on minus n to the k is also is considered diagonal if and only if every diagonal tuple is related to every tuple in both directions, xry and yrx. So you're really absorbing all the diagonal ones. This comes up for technical reasons. It's pretty harmless. To do this, because we want to look at EMV, and we want to look at EMV only for relations. We only want to work with relations that are diagonal and where the dimension is at least 2. You'll see that here. This was what I'm trying to say. All right. And of course, the notion of chain makes sense for a sequence rather than just this set. Any two distinct terms are related, uh, is the definition. All right, now we need to have a way, given a sequence of k tuples, we need to have a way of getting a new k tuple out of the old, in some sense, sort of out of the old ones. we know that we need to sort of do that. Um, and we use the following idea. So first we want to have an enumeration of the elements of minus n to the k. Well, but first we want a master list. No, I'm sorry. Let's start again. This is not what I meant. I need to look at this at the k tuples of positive integers because I'm going to use each positive integer for a location in a complex tuple. I'm going to look at these integers in terms of location, position, and sequences. So I need a decent way to enumerate all the finite sequences of length k from z plus. And that's called alpha 1k to alpha 2k, alpha 3k, and so forth. All right. And we're looking for this function called next. This one here. All right. So here's the key definition. If I have a bunch of, long list of k-tuples, I want to define what I mean by the next one. The next one is obtained from looking at the concatenation. So we look at the concatenation of x1 through xk, and we extract out the subsequence whose indices are according to u. Wait, it's a subsequence of the concatenation, which is u, but the next is it's the index is I1 through IK. I1 through IK, where I1 through IK is the rth finite sequence, right? Okay, does that make sense? In other words, I have a long sequence of k tuples. I make it just a long sequence of rationals. I just do that first, and then I extract, given the length of the finite sequence of k tuples, which is r. I then look up the rth the rth sequence of length k of positive integers, that is, and I use them to tell me where to jump around to get the final tuple. Okay, I hope that understands. Okay, then we have this substantial definition of what a resolution sequence is: x1 through xr. First of all, it's got to be a chain, and r has to be at least 2n. We require that the first two times n, terms are prescribed exactly and conveniently. They're these diagonal elements, I through I and minus I through minus I. All right. Now, what do you do when you're higher, at or equal to 2 times n? So below 2 times n, it's just these diagonal things on the numbers from minus n to n. Now here, what you do is, so if you're doing this at an even place, in other words, an even index k-tuple, then what you do is you want to use this for density purposes. What you want to do here is look at the first two terms. You first look up next. You're always going to look up next. You look up next, and you look at the first two terms, if the first two terms, if the first one's less than the second one, you return a diagonal that's strictly in between. You return a diagonal that's strictly in between the first and second terms, and then if that doesn't work, you resolve. I'm sorry. If that doesn't work, you give the default. You give this default. In any case, you're going to give out. You're only going to give out a diagonal. The even indexed x's are all going to have to be diagonal. The odd number x's. This is what you use to do resolutions. So x2i plus 1 is obtained from taking the next and resolving the next in the following sense. X2i plus 1 is either y or blocks y. It either y or blocks y. Okay, so you can see how this is a finite approximation to actually being resolving every term or being maximal in the restricted sense, right? Okay, so this is a good notion of resolution sequences. And what does it mean for a resolution sequence to be embedded? Well, I take the following definition. You look at the sequence of objects and you look at what the partial function here. You want to take the resolution sequence and close it, or actually just take the image of it under the things that embedded resolutions are related to, right? In other words, just shifting over, keeping the negative part. This is what you want to do. You need to know that when you do that, you still have a chain. Okay. When you do that, you still have a chain. When you take the images and the inverse images of this special function, you basically have a chain, maximal chain. Excuse me, you basically have a, I didn't say it right, you have a p-shift embedded set or sequence. You have that. I mean, that's the definition. Sorry. When you take the image under those functions, it remains a chain. That's the point. It remains a chain. All right. So an infinite embedded resolution sequence is just an infinite sequence of these k tuples where each finite initial segment is of length at least 2 times n is a resolution sequence. So that's how I linked this work to the earlier work about infinite things. Okay, so all right. So we have this notion, we have this statement ERS. In every order invariant diagonal relation on every minus n and k, where k is at least 2, there are embedded resolution sequences of every finite length greater than or equal to 2. All right. And then what does ERS infinity say? That I can actually get it to be of infinite length. All right. Now, how do you show that ERS is the same as ERS infinity? This is a straightforward weak Koenig's lemma argument. You see all of these finite resolution sequences form a tree under extension. And if you look through the definition of uh, of these resolution sequences. If you look through the definition of p invariant maximal chain, you see that when you apply weak Koenig's lemma uh, or compactness, you wind up with this ERS infinity. Well, it's not quite a maximal. It's not quite a maximal chain because the effective domain, is not necessarily all of minus n. Uh, you may have gaps. However, it will be dense. This is the point. It will between any 2 points there will be a third. Between any 2 points there will be a third. This allows me to go from ERS infinity to EMV. See, that's the point here. And why do I have density, so to speak? I don't have why do I have this density? It's because uh, of those clauses that I was putting stuff in between and making that constant. That I was doing that over here. Uh, okay, now yeah, so the easy result is, well, first of all, there's this compactness argument or weak Kyrgyzstan argument that ERS is equivalent to ERS infinity. But ERS and ERS infinity are very close. The only issue between them, as I was mentioning, is that you get density between any two is the third when you're over here, but you don't get that it's actually a whole interval. It's just dense, but that's good enough. You show that actually is equivalent to uh, getting EMV. This is the pure compactness. This is what I'm talking about here. Yeah. So you get this. I call it EMV minus when you restrict the relations to be diagonal, having that diagonal property plus the dimensions at least 2. All right. So the way this is done is I show EMV minus implies EMV. That's the thing where this thing is just density, and this thing is that it's got to be uh, minus n. You see, this is a tricky point. And then from EMV to ERS infinity is very easy. But how do you go from ERS infinity to ERS? That's also not hard because the restriction. Well, that's done there. This is trivial. I'm sorry. ERS infinity implies ERS is totally trivial. This says there's one of infinite length. This says there's one of every finite length. And then you want to show this, that ERS gives you EMV minus. And that's also easy. The hard thing here is this next one. Yeah, the one that I haven't finished checking. I have to think about it, whether I need to fool with FEM. Yeah. All right. There's an intermediate construction that's important for this, and that is if I have a relation on k tuples, I can make another relation on t times k tuples, which essentially is the chain relation. In other words, x1 through xt x1 through xt is equivalent to y1 through yt if and only if when you put them together, you get a chain in R. So this is the sort of chain construction. And this, my idea is that this is the kind of better relation you want to use when you use FEM. So I'm going to use FEM on such a FEM on one of these chain relations. And that's how I get the power that I need to reverse. All right, I think that's it for today. Yeah. Okay, so I'm finished.